Okay, thank you for the introduction, and it's good that I'm the last speaker, because if the answer to my question turned out to be yes, then we would have had to cancel the rest of the workshop. So no one's at risk of that now. But many of the themes that I want to talk about, Ian already did a really good job of making the case for them earlier today. But I think you'll see some of the message that I have is quite similar to what he had. Before I get into that, it is a momentous day in our community's history, at least somewhat related to this. So the GDPR, the reason you've been getting all these wonderful emails from companies telling you how much they care about your privacy is because of this law that goes into effect May 25th, but in Europe it is already May 25th. So it has actually already been in effect for about 30 minutes as of the time that I'm speaking. As far as I know, the internet has not yet shut down, but we've all been paying attention to the talk, so I'm not sure if that's the case. But it is actually a really interesting opportunity for our research community. So I was at a meeting last week where David Basin talked about some of the issues for programming analysis and policies related to the GDPR, and had this quote that it is a nightmare for managers. You can see that when the complaints come in, you have 72 hours to respond to them. So assuming one came in right when the law went in effect, that clock is counting down. But it is a researcher's paradise. It opens up lots of interesting research problems and things that, because of the law putting pressure on industry, there's going to be strong interest in. And one of the things in the law is this Article 22 that talks very specifically about automated decision making, and the kinds of things that we're using machine learning models for now have to be subject to regulation and questions about whether they're making decisions in ways that are harmful to people that can't be justified. So I think this is something definitely I hope people in this community are thinking about. It's not the main topic of my talk, which is focused on adversarial examples. And the field has really exploded. It's great to have this big workshop. And in many ways, it's a very new field. So Ian showed the picture of the bus from this paper that kind of kicked off all the excitement about this area about 5 years ago. If things keep on the trend they are, they're expected to be over 1,200 papers on adversarial examples published in 2018. And I don't know if there's maybe a little delay because people aren't posting their papers today while they're at the workshop, but I think that trend is actually continuing to accelerate, so it may end up more than that. Of course, the general problem that we have here didn't start in 2013. Adversarial examples go back long before deep learning. And there's a great paper from Biggio looking at the history of adversarial examples in malware detection in machine learning going back at least a decade. Of course, they go back even further. We had adversarial examples, and I'm putting before machine learning in quotes there, because certainly machine learning goes back many, many decades. But before at least it was used in the way we're thinking of it today, or used in the security community, there was a huge arms race between malware authors and malware detectors. And of course, it goes back even before Oakland, which for those who might be new to the community or just here for the workshop is an ancient conference that goes back almost 40 years. Well, the logo for Oakland is an adversarial example, right? So this is the Trojan horse. If you haven't seen Virgil's paper, it's probably an archive. But he talks about having a machine that is being used against walls, spying on our homes, coming in this disguise. So it certainly goes back a long time. So how should we define it? So we had a definition this earlier today from Ian that is really the right intuition, right? Adversarial examples are inputs that an adversary creates with some intention. Unfortunately, it's pretty hard to use that as an operational definition, right? We don't have a pool of adversaries we can ask to have evil intentions and create things for us for our experiments. So we end up with different notions and different definitions. They all have the notion that there's some difference between the space that the classifier is working in and the reality. Right? So you have, for the Trojan Wars, well, the judgment of the Trojans identified this example as a gift. In physical reality, it hid an invading army. In malware, we have a malware detector. In the classifier space, an example is identified as benign, which in reality performs the malicious behavior that the adversary seeks. And in image classification, we typically have our reality space is based on human perception, and the classifier sees something that matches a given target, which is different from what the human sees. So I'm not going to talk more about the Trojans. That's a little outside the scope of deep learning. Next, I'm going to talk about malware, and we've certainly heard some examples of deep learning and malware earlier today, and later I'll talk more about image classification. So the nice thing about malware is the reality space is something we have ground truth for. Right? It doesn't depend on something as fuzzy as human perception. So if we're lucky, we can train a classifier that will accurately distinguish benign and malicious examples. And the oracle space, we might actually be able to determine in an experimental way something very close to what the real reality space is. And that could be running the malicious sample or the sample in some environment, seeing what it does. The closer that environment is to the real victim's environment, the better. So with this, we can define an adversarial example as given some seed, the adversary wants to craft a modify that seed in some way to produce an example that is classified by the classifier in the target class. If it's just a malware classifier, there's only two classes. It's benign or malicious. So the target class is benign, where the behavior that we care about for the X prime that's crafted with adversarial perturbation and the original sample are the same. And that means that the adversary's goal is to preserve this malicious behavior, but produce a sample that's classified as benign. And so there's no real requirement on how X and X prime are related, other than X, the original seed, defines the behavior that the malware author wants. So anytime we have a definition, that suggests an attack, right? So that tells us what the goal of the adversary is. And in this case, the generic attack, if this is our definition of an adversarial example, the generic attack is to find some way to heuristically explore that input space to find an X prime that satisfies that definition. So the first work that got me interested in this space was attempting to do that, and we used a method based on evolutionary search. This was mostly work from Weilin Zhu, who's somewhere in the back here. And the idea was we're just going to mutate. We're going to take our seed. In this case, we're focusing on malicious PDF files that is classified as malicious. We're going to mutate that seed in ways to try to find a version of it that is now classified as benign, but has the malicious is now classified as benign, but still has the malicious behavior. So in order to do this, well, we have to have some way to generate variance. In this space, we're not constrained by any distance metric, but we need some method of finding variance that we think will still have the same behavior. And so the method we use is genetic programming, where we just select random nodes. So most malware can be turned into an abstract syntax tree. For PDF files, this is really easy. They have a nice hierarchical structure. So you pick a random node, you pick a random operation, and you do that. So you could delete that node. You could insert a node. If you insert, you need something to insert. So you need a pool of other nodes that are likely to make a PDF more benign. And so we can collect those from benign PDFs. And so you'll select a random node to insert, or you can do both and replace. So what we're going to do is search for promising variants, ones that are looking more benign than the original one did, that still have the behavior. And that means we need some way of selecting each round the variants that seem most promising. And this is the standard approach with genetic programming. We're just going to take in each sample, and we're going to evaluate it with some fitness function, and we're going to select the ones that seem to be the most fit. And in this case, the fitness function is going to take in two inputs. It's going to take the output from the classifier, which the closer it is to being benign, the better. And it's going to take the output from the oracle, some way of saying, is this actually having the behavior we want? For malware, we can do that. At least in many cases, we have the big advantage as simulating what the malware author would do. We know the behavior we want. It's not nearly as hard as writing a malware detector when you don't know the behavior you're looking for. So all we have to do is simulate the program or execute it in some environment where we can monitor it and see if it has that behavior. If it does, it's malicious, it has the behavior we're looking for. If not, we assume it's useless. So that means the fitness function is just going to be taking the classifier score. If it's malicious, we look for ones that are more benign. If the behavior is lost, we assume we're never going to get it back again, and that means it's the lowest possible fitness and we want to get rid of it. So it turns out this works pretty well. So you can see for the 2 target classifiers, out of the 500 testes, all of them we do find evasive samples for. In many cases, it's really easy, right? So for 162 of the seeds, very simple transformation worked, just inserting a page. So if you don't read raw PDF, all this is doing is inserting a page in the document. And the reason this works is because the training set that was used to train this classifier, a lot of the malware in it did not have any content, right? All benign PDFs have some content. So it is not a very useful, it's a signal that's useful when you train on current malware. It is not at all a problem for a malware author to add pages to their malicious PDF. Right. In other cases, it was harder. Some required quite a lot of transformations to find a version that still had the same malicious behavior, but was now classified as benign. So I said, that having a definition suggests an attack. Attacks tend to suggest defenses. Of course, the defenses that are suggested by particular attacks tend to always break. Right? This is kind of the second oldest principle in security. So that's true here as well, right? So one defense you might suggest to evade one defense to prevent these evasive PDF malwares would be to change the malicious threshold. If you look at the evasive samples that are found, most of them are very close to the 0.5 threshold that was set in the search. But of course, if we set the search lower, we can set that threshold lower, those would still be malicious, then we can do the search and we can find ones that hit a lower threshold. At some point, you can set the threshold low enough that every PDF is malicious. That is probably not a useful classifier. Maybe it is if you don't like PDF files. Okay, so the other thing that this might suggest as a defense is, well, what we needed to make the fitness function work is we need the score from the classifier. Right, so maybe the solution is to hide it. That, of course, also does not work, and there's a paper from a group in Singapore about how you can make a strategy work where all you get is the binary output, whether it's malicious or not. And you need to use some clever techniques in hill climbing to make that work, but you can still always find evasive samples. Okay, so we don't want to have defenses that are responding to attacks, and Ian made this point many times earlier today. We need our defenses to be based on the definitions, based on understanding what the adversary's goals and capabilities are, and thinking of that as the way to design a defense. Okay. So now I'm going to turn to talking about images. Images, we have a real problem with our definition, right? So that the definition we want is that we have a sample that's classified as some target by the classifier and perceived as something else by a human. But humans are very bad at perception, and we've seen lots of examples about that. Hopefully people have not been spending too much time listening to the Yanni Laurel thing, but if you haven't, you should try. I was going to play it and see how much of it is based on the speakers and other things, but I will spare you from that. But human perception is bad. Even if we said, well, human perception is good enough, we're going to take what the majority of humans perceive something as. It is fairly painful and expensive to have an army of humans telling you what humans perceive something as. So the alternative that's been adopted in most of this work is to have a notion that we can define the limits on the perturbations that won't change how a human perceives things. So we have a notion of the classifier space. We have a notion of the human space. or the oracle space that models human perception. What an adversarial example is something where if we perturb the input a little bit, in classifier space, it changes the class. In oracle space, it's expected to be in the same class. Of course, this is a very misleading visualization in lots of ways. So one of the dangers of visualizations like this is we try to turn a high-dimensional space into something that we can fit on a slide with 2 dimensions. Maybe if someone's really artistic, they can get 3 dimensions on a slide, but no one knows how to get thousands or millions of dimensions on a slide. It also, gives the misleading impression that, well, this is kind of just a few of the samples are near a boundary, and you'll be able to do this, when it turns out that all samples are near boundaries once you're in an actual classifier space. And it also looks like, well, maybe all samples are near boundaries, but they're only near 1 or 2 class boundaries. But what we've seen with targeted attacks is you can target any class. So it turns out pretty much every sample is at least fairly near every class boundary. And so these kinds of visualizations can be very, very misleading. Okay, so this means our adversary goal is to find some small perturbation that changes the class for the classifier, but is imperceptible to the oracle, which we're trying to hope is something like human perception. And this is the definition that goes back to Biggio's paper, at least, and there may be even earlier ones that are very similar, that is trying to minimize the distance you need to change the class of the sample. And one challenge with definitions like this, if your goal is to minimize, and that probably is a useful goal in many cases, it doesn't give you a way to say yes or no, this is an adversarial example, right? It just says your goal is to minimize. So the definition we usually need if we're looking at things as whether an adversary can succeed has to have some threshold on the maximum distance. Otherwise, you always have an adversarial example. So that's what I think is the most commonly used definition. Is very similar to this, or stated in a few different ways, but it's basically that we have a seed sample. We're trying to find an X prime is an adversarial example if it satisfies these 2 properties, that the class is in the target class, which could be any other class besides the original class for untargeted. For most security problems, targeted attacks are much more interesting than untargeted. And in some metric space, which tends to be some fairly simple metric space that's easy to measure, the distance between the seed and the adversarial sample is below some delta. So this relies on this big assumption, which is very problematic, that the small perturbation doesn't change the class in reality space. There's several other problems with this definition. Right? So first of all, if your model has boundaries and it's continuous, well, it has adversarial examples, right? So any claim of having a robust model, if this is your definition of adversarial examples, the only way to satisfy that is to have no boundaries, and that means you only have 1 class. So it's a robust model is not a useful one, at least according to this definition. It's also a very unnatural limit on adversarial strength, and Ian made this point several times already, that, yeah, if we get this strong result and prove that our model is robust for some input points with some definition of adversarial strength, unless that also gives us some intuition that some slightly different way of defining adversarial strength or allowing it to perturb 1 extra pixel won't change things, it's not a very useful guarantee, even if it is a guarantee. And the final problem with this, it kind of doesn't really capture what the adversary's purpose might be in finding these adversarial examples. It seems to suggest that their goal is to find them, to find as many as they can, or maybe just to find one, but it's not clear what the purpose is or what the value is to the adversary. But I think this is the definition that's most widely used. So I tried to, from all the papers in this workshop, tried to figure out what definitions people were using. I shouldn't make that a mystery. It was often stated very clearly and well in the papers what definition they were using. And this was the predominant one. So 6 of the papers were using this. The ones in other domains were often able to use the Oracle definition, more like the malware, especially ones in the malware domain. And then there are papers that are not about adversarial examples, which is good. This is not just an adversarial examples workshop, if it might seem like that from the keynotes. But the building classifiers, interesting, most of the classifiers, and I won't give a count, but I think only one actually talked about adversarial examples. So that's, I guess, a sign that it's still a big challenge to build classifiers that work well without worrying about adversaries, but it's also a sign of we need to start always thinking about what adversaries will do to classifiers. Okay, so now that we've said this is a bad definition, we're going to mostly still do things with it, because this is the definition that is established, but I think it's definitely something we need to really think about what the definition should be, as well as how we're going to measure adversary success, and I'll get to that some more later. Okay, so I want to show a, we can't quite see the light bars on this, but the what happens inside a network. So it's most of the work so far has looked at sort of just the input and the final layers. There's starting to be research that looks inside the network, including some Nicholas has been doing with the deepest K nearest neighbors, and some a group at UC San Diego has done. And what I want to do here is visualize what's going on inside a network to try to understand a little more what's happening with the adversarial perturbations. And so here you can see for each of the input layers, the distance between the adversarial example and the original seed. So you can see that it starts out very small, and that distance increases. If you could see the lighter color, you'd see that there's a band of the percentiles, but by the end, it's almost all of them are ending up in the wrong class and far distance from the original example. I should mention, so Jonas is here as the student who's been working on these visualizations and how we might use this information in the network. So this is what an adversarial perturbation looks like. What a normal perturbation looks like, if we just add random noise, is very different. Right, so if we start with the same amount of random noise, you can see at some layers it does increase, but it never increases enough to change the output class. At least it's very rare that it does. And you can see that it ends up shrinking back to the same as the normal for this amount of noise. Very different from what the adversarial example does. And of course, this depends on the adversarial method. So that is FGSM. For the Carlini-Wagner L2 attack, you can see the change starts out, so here we're starting with the same small change, which is much smaller than the FGSM, but it gradually increases through the network until finally at the final layer being completely in the furthest away distance. Okay, so if we have a definition, it should suggest a defense. In this case, so we talked about definitions suggesting attacks. We don't want to suggest attacks. We don't want to use attacks to suggest defenses. We want to look at definitions to suggest defenses. So the defense that this definition suggests is that we need to, if we're assuming the adversary is making a small perturbation in some space, what we want to know is there some way to undo that perturbation and see how the model performs? So that's the idea behind the defense that we call feature squeezing. So the idea here is that instead of just running the original model on the sample, what we're going to do is modify the sample in some ways, with the hopes that the ways that we modify the sample will undo those perturbations. And so we're going to do some pre-processing on the sample, run it through the model. Maybe we even change the model. And our goal is to have a preprocessor that's going to coalesce inputs that are similar into one point. So we're going to reduce the space the adversary has to search. And we hope that this will barely change what the model does on legitimate inputs, but might have a big impact on the adversarial perturbations. It should destruct them if we have the right preprocessor. So that's our goal, right? And if we're doing this effectively, it's going to coalesce many possible inputs into one point that will always classify as the same way. So there's no value to the adversary in searching that space. All of those end up in the same point. So what's an example of a squeezer? Well, a really simple one is just to reduce the bit depth. Right? We can discretize the input. So instead of having 256 possible values in a grayscale, we could have 2 possible values and just round the intensity to either 0 or 1. For certain kinds of data like MNIST, this works really well. Right? And MNIST is a very strange data set. It started out as black and white images that were scans of handwritten images in black and white that were then anti-aliased. So in some sense, this is kind of the ideal data set for this technique. But it's not a data set that is representative of most data sets. But there are lots of other squeezers that could work on more complex data. And we've done some experiments with spatial smoothers. There are many other more complex ways of pre-processing inputs that can potentially undo adversarial perturbations. And so I will make the very bold but vacuous conjecture that as long as we stick with this definition of adversarial examples that are limited by some simple distance metric, then there exists some feature squeezer that can always detect them, that we can always find some transformation that will undo the adversarial perturbations in a way that will distinguish the adversarial inputs from the normal ones. And if we can find the right ones, well, they might work to give us a very high detection rate. So for our MNIST, it's pretty simple setup with 2 squeezers. Will work against at least some known adversarial examples. Certainly this is a long way before making any claims about what an adaptive adversary can do. But you can see what's going on in the network from this, is that if we look at the distance between, so unlike in the earlier graph I showed you, we don't know the original seed, right? Obviously, if we knew the original seed, it would be very easy to distinguish the adversarial examples, but it would not make sense, because why would the adversary give us the original seed? So in this case, what we have is some input which may or may not be adversarial, and then we squeeze it. And we can compare what the model does on the original input to what it does on the squeezed input. And you can see that that separation doesn't start to happen until later layers, but often we do get a pretty good separation. In the case of the Carlini-Wagner attacks, because the distance is so small, it's actually enough to get a very accurate division. In the case of other attacks where the perturbation is bigger, there's still enough to get a good distinction for a very simple scenario like MNIST. So we can set the threshold where we see the difference between the legitimate and the adversarial examples and have a pretty reasonable detection rate of which ones are adversarial. For ImageNet, it's trickier. At least we need more squeezers, and we don't have quite the nice separation that we would like to have. But we have enough of a separation to have a reasonable detection rate across this set of different adversarial techniques. So this isn't targeted to a particular technique, but trained on a set of what we think the distribution of adversarial techniques might be. Okay, so how should we evaluate defenses? So certainly a first step, and just trying them on known attacks is definitely necessary. If they don't work on known attacks, you definitely do not have a defense. But that's definitely also not good enough to have any confidence that a defense can work. So unless we have a scenario where we have some reason to think that adversary doesn't care about attacking us, which is probably not a very interesting security scenario, we have to assume that adversary can adapt. And at least the generic way for an adversary to adapt is for them to incorporate the defense in the loss function. So instead of just minimizing the goal of misclassification and the distance, they can incorporate something that measures evading the defense or measures what the defense is doing into the loss term. And in this case, for evading a detector, it's adding a term that corresponds to whether or not it's detected. So this means that to find examples, you need bigger perturbations. So in this case, the attack is unbounded. So we'll always succeed in finding one unless it runs out of time, and in a couple cases it did run out of time, but needs to do bigger perturbations to satisfy that more complex loss function. And this gets into the human perception question of whether these look enough to be successful adversarial examples or not. But at least in terms of if you bound the distance, it looks like it's getting much harder for the adversary to adapt. But they can succeed sometimes, and it scales as you scale the adversary power. you need bigger transformations, but you can still find adversarial examples that succeed. Of course, this is the most generic adaptive attack, right? So certainly this does not exclude more clever things an adversary might do based on design a custom attack around the defense. Just assumes that they know about the defense and can incorporate it into an existing attack. Okay, so the other thing that I want to do is look at, so if we're evaluating the defense based on how often the adversary succeeds, right? We're getting, maybe it looks good because the adversary is only succeeding a few % of the time, or 10% of the time, or 20% of the time, which at least in the space is considered a pretty good result for a defense. That really needs to question what the adversary's goal is, right? Because in most areas of security, if the adversary succeeds 1% of the time, that is a huge failure for your defense. That is not considered successful. So one way to revisit that is to think, if we have a domain where the goal of the adversary is not just to find one, right? I think if the goal of the adversary is to find one adversarial example, and they're not constrained by the set of starting seeds in any particular way, that seems like, at least based on what we know how to do now, we are very far away from being able to make any claims that we could prevent an adversary from finding one. And certainly against existing models with these definitions, against any model with this definition, adversarial examples always exist. So in some domains, maybe it's much more realistic to think about the adversary's goal is to find many adversarial examples. Right? If the goal is to find many, then what we have to think about is what is the cost to find many. And we can think about that in different domains. In the case of a Whitebox attacker, the cost to the adversary is primarily the computational cost. How much effort is it for them to search for the adversarial examples they're going to use? If it's a Blackbox API attacker, then the cost is more about the number of interactions they have with the model. Right? They're going to need queries to the model. Maybe they use those queries to build a local model that they can use for transfer. Maybe they're using those queries as part of a direct attack, which is the version we'll look at. So for the Blackbox cost, the real cost is the number of interactions, and what we care about is not the average number that you need to find an adversarial example. What we care about is the total cost to find some number of adversarial examples, because that's the adversary's goal. So it matters how much that cost varies across your target seeds, right? And that assumes you do have some notion of what the target seeds are. So we're going to look at results for an attack called Zoo, that is a Blackbox attack based on learning gradients through queries. And what we see is there is a big variance. So for these results I'm showing, we're assuming that the adversary retroactively can decide how to use their resources, right? So if they used all the resources on the easiest to attack seed, that would be the first one in this graph. And as they go down the graph, they're needing to attack more seeds. So if they just had to attack if they had to attack all 100 of these seeds, for MNIST, the average cost is 117,000 queries. But if they only needed 20, the average cost is 50,000. And for CFR10, it's much easier to find adversarial examples, but the ratio is similar. And if you look at them, you can kind of get a sense of why. So these are the MNIST examples, where the least likely class from 0 turns out to be 1. They're ones that are easy. There are 14 in the sample set where even after the 256,000 queries, there hasn't been a successful adversarial example found. For the CFR10, it's going from airplane to frog. You can see that the ones that are easy have a lot of color and a lot of noise and distraction in them. The hardest ones are ones that have very plain backgrounds. Right? But some seeds are easier to attack than others. And this is true also for the Whitebox attacks. So here we're looking at the number of iterations. So this is the computational cost. So a big caveat for these small ones that we're so far able to do experiments on. All of this cost is orders of pennies, right? You could do the whole attack for all of these. It's not a huge amount of computation, but this is also in a simple domain for small images. So the cost does scale. And assuming that this variance continues to scale, then it's relevant that the cost scales. And so the average cost varies greatly. There's some examples that are really hard to find, for some seeds, it's really hard to find adversarial examples. For most of them, it's quite easy. And zooming in on the easiest ones, the easiest 20, you only need 2 or 3 iterations to find adversarial examples. Okay, so this doesn't tell us if it affects the attack yet, because these results are all based on looking at all of them, running the attack on all of them, and then sorting based on the difficulty. So for this to work for the attacker, they need to be able to guess in advance which ones are hard and which ones are easy. So it turns out that they can, that a very simple greedy strategy works quite well. So the simple greedy strategy is just based on the initial prediction vector, which we're assuming the adversary has, or they could get from some other model if they don't have it for this model, but many of the APIs do provide the full prediction vector. You target the ones that are closest to your goal first, and you target them in that greedy order. And this does pretty close to the retroactively optimal if you knew that total costs before you started. It is definitely, orders, about, depending on how many you're targeting, about a quarter of the cost of targeting if you picked your seeds randomly. This is for the black box attack. For the white box attack, the gap is even bigger, right? That at least for CFAR10, if you can predict very well the ones that are easy, and they're much less expensive. So I think if we're thinking in a domain where our concern is, can the adversary find many adversarial examples inexpensively, we need to think about the cost of finding a batch of them, not just looking at the average cost of finding one or the % success, if the adversary can do things. And so if you look at the Madre Defense, which I think is considered probably the most successful defense, although maybe what Ian talked about this morning is now the state of the art, but we haven't been able to try against that yet. Even against that defense, which is very successful against average attacks, even against ones targeted to that defense, there are examples that it's very easy both to identify that they're easy. So these are organized by each batch is the set of examples that are predicted to be easiest. So the ones that are predicted to be easiest, for MNIST, at least the first batch, the adversary can get success about 50% of the time, and it does vary based on the class. For CFAR10, the Madre Defense doesn't work so well in general, but it still has this property that the adversary can find the easy ones and attack them. Okay, so to get towards my conclusion, so we're in a great area that's exploding quickly, lots of interesting stuff going on. It's also a really strange area as far as security is concerned. Right? Normally in security, we're talking about attack successes, needing 128-bit keys, and if someone finds a break on your crypto system where they can reduce the attack cost to 2 to the 125, that's like a huge break, and everyone runs screaming for the exits, and your encryption algorithm is thrown out, right? And we're more in a domain where the attack success probably is pretty close to 1. In the case where it's black box, maybe it's close to half or a quarter. But this is a very strange domain for security research. So that's something where I think we can make progress, but we have to think carefully if improving that a little bit is actually the right thing to do, or we need to think very differently about what we're doing. There was a great talk at NIPS from Ali Rahimi. I hope some people have seen this already. If not, I encourage you to see it. And it's only about 20 minutes long. And he talks about machine learning being alchemy. And this got quite a bit of attention. Some people were kind of offended by it. If you can see Jan Lukens' quote. I was offended by it also because I am a proud alchemist. So alchemy is underrated, but I think we've got a long way to go to actually catch up to alchemy. So the alchemists, they didn't succeed in their goal of turning lead into gold, but they had a very well-defined, testable goal. Right? They knew they didn't succeed. They didn't claim they succeeded when they didn't. So we're not quite at that level yet. They did have a theory that was established. It turned out to be completely wrong, but at least they had a theory they could talk about. And they had a way of doing methodological experiments, and they had lab techniques. So there's a lot that the alchemists have that we're not quite at that level yet. But hopefully we're making progress towards that. In terms of the question of sort of how to define adversarial examples, or whether adversarial examples itself is an adversarial example. So we're in the domain of academic research, right? Our classifier space is conferences and workshops like this one that are a lot of fun, and we, from the number of people coming to this workshop, it's definitely, getting classified as an awesome, cool area, and that's good. For if you're enough of an academic, that might be your reality space as well. So that's good, but that's not everyone's reality space. I think most of the world lives in a different reality space, and it's still a question whether this is a research area that is working on things that are actually the right problems for real systems and society, and building ideas that are, I think, certainly ideas that are exciting, whether they have application beyond and the way Ian talked about. We've been sort of working on this game that he set up about 5 years ago, whether that's going to lead to the big ideas that will help us make progress. So thank you for your attention. I'm happy to take questions, and I have one bonus slide if you would like, because I saw that this actually came out today, the report on the Uber incident in Arizona, which is also a case where this is not an adversarial example in the sense that there was no adversary creating it. And I think one of the reasons to do work in this area is because of adversarial examples being, if we can solve that problem, that's kind of the worst case for what might happen in nature. But you can read about, so the NTSB report, it says that the classifier classified the pedestrian first as an unknown object, as a vehicle, then as a bicycle, with varying expectations of future path travel. But it did classify it and decided that they should turn on the emergency brakes. But I'm guessing they get too many false positives, so they don't actually let the autonomous system turn on the emergency brakes. So it didn't actually emergency brake. That seems to be what happened where the pedestrian was killed in Arizona. So I'm happy to take questions.
Questions? Oh, come on. No one? Okay.
Hi. So I really like the feature squeezing from the idea behind it. The big problem so far that we've seen is that most things that you try for feature squeezing tend not to be so effective. And so in particular, all of the defenses you put on that slide were in fact completely broken. That like you might try for feature squeezing, so JPEG compression and magnet and all of those other ones were broken. I'm wondering if you know of anything that you can think of that like isn't just bit depth quantization, which clearly works somewhat, but I wonder if you have anything more to say there. I don't know quite what I want, but I do like the idea of feature squeezing. It's like it makes sense to me, but I don't quite know how to make it work.
Right. Okay. So to paraphrase Nicholas' question, so all the defenses, he's been able to break them all, right? And I hope people have seen that the paper that you posted, that sort of every defense other than the Madre one that was in ICLR, he was able to break them in a few days or before they were actually posted, and the defenses in CVPR. And it is definitely a really important question of saying, like, how can we have any confidence in these defenses when the ways that they tend to be evaluated lead something that looks like a good defense to be broken very, very quickly. So I think where my hope is where this goes, and I think the hope that I have with having a framework like feature squeezing. So first of all, any of the preprocessors outside of framework have a huge risk that they actually give the adversary even more power, right? So if you don't include the part where you're comparing what the model does on the original input to what it does on the input after the preprocessing, you are now giving the adversary who knows about the preprocessor wonderful new opportunities to construct attacks that are even more effective, right? So I think it's very dangerous and clearly the case that all of these preprocessors that don't include something else, either they're doing so much preprocessing that they're losing accuracy on benign examples, or they're giving adversaries opportunities to attack you. You can think for the simple example of the bit depth filter, now you've got an image that looks entirely gray that can map to anything you want if you're doing discretization of one bit on a grayscale image. Where I think there is hope is if we can think about how to compose the filters in principled ways to know that because of having multiple filters and the different transformations we're doing, that certain classes of adversarial perturbations cannot, that there's no perturbation you can find that wouldn't be detected by one of the filters. So I think there are, this still would be limited based on the type of perturbations we're assuming the adversary can do. But I think there are ways to compose filters that would give you some kind of principled result. The other thing you can do with filters, which I think is still fair within the, so assuming the adversary knows anything, because in cryptography we still don't assume the adversary knows the key, right? It's legitimate to have a system where the adversary knows everything about its design, but you can use randomness. And there are definitely lots of opportunities within preprocessors to use randomness, especially in an ensemble framework like the way it's done with feature squeezing, where you can use randomness in the filters that gives you an advantage over the adversary. That is also something where some of it depends on your definition of what it means for the adversary to succeed. So even the ones that are broken, at least the ones that seem broken in that you can find the adversary examples, at least the distance required to find them goes up, right? And if you add, depending on what the preprocessor is, that distance may go up by enough that for some domains and based on some ways of looking at them, they're no longer adversarial examples. So I think that's a big question in terms of deciding what it means to be broken. Also has to encompass some idea of how big the perturbations can be for it to be considered as a successful adversarial example. And so another way of looking at the defense is if it means the attacker has to make bigger perturbations to succeed, at some point that might be a strong enough defense to be useful. That gets into the question of, well, where do we cut off? If it's meant to model human perception, we know that none of these LP norms are a good way to model human perception. So there's no clear way to know how to cut that off.
Since the title of your talk is about adversary examples, so from one point of view, so why are we surprised that adversarial examples exist? Because none of these classifiers have 100% accuracy, even on the normal test sets. On the MNIST, the best accuracy is about 99.4. On CIFAR 10, it's about 90%. So even on the normal test examples, 10% of the examples are classified incorrectly. And if we assume that the test data set is representative of the normal things we see in the world, then we expect the classifier to make the wrong decision on 10% of all the images. Then the job of the attacker becomes how to find those 10% examples. So I guess the only difference is that for the real adversary examples that the community has been worried about, they have to be derived from the normal examples by some delta. But if you remove these constraints, then it shouldn't be any surprise that we can find a lot of examples. The examples that will make the classifier misclassify. So what's your take on this? So is our way of defining adversary examples artificial?
Yes, so I think that the simple answer is we should build perfect models, and then we would not have any problems.
Correct.
If we don't know how to do that, then the one thing I would say is what's important for it to be an adversarial example does have to have something to do with the intent of an adversary. So I think untargeted examples are usually uninteresting and presumably the natural mistakes that the classifier makes are effectively untargeted adversarial examples. For an adversarial example to be useful for an adversary, for most purposes, it needs to be targeted.
Not necessarily. So in your bonus slides, if the classifier has a binary input, whether something is a pedestrian or not a pedestrian, then any attack, since it's binary classifier, then any attack would work.
Right, and that's a case where there's no adversarial intent as well, right? So in some sense, that's not an adversarial example, but it's a motivation for saying, and I think you're right, that's a motivation for saying we should really care about untargeted attacks as well, or at least making models that are robust to inputs that are not targeted attacks, because if we're viewing it as a way to get at sort of the safety and regulation issues for using AI systems, then it's really a question of we need to get the correct result on those inputs. So I think that definitely is a ambitious goal, to never get the wrong result on an input. I think there are ways to define adversarial examples that at least give us some hope of making progress without. So I think if we define the adversarial examples in a way that just is the same as building a perfect classifier, then we don't need a separate sort of conference. We shouldn't be in the security community working on this. This is the same as like the machine learning community's goal for a long time. But I think there's something very interesting about viewing it as an adversarial problem that is quite different from just the goal of building more accurate classifiers. And some of that is because, there are domains, and especially the security malware domain, where it is clear that it is an adversary and it's clear what their goal is. And there it is something where I think part of the question is, it is also the case that the classifiers are wrong enough of the time that you don't need to do a real sophisticated machine learning evasion attack to find an adversarial example, that there's enough malware that gets through malware detection without needing to do anything that sophisticated. But at least anticipating future progress in the classifiers becoming more accurate, then it's definitely will be something where the malware authors are motivated to look for adversarial examples, and certainly the methods that they might use are going to be methods that are based on targeting some particular adversarial goal. So I don't know if that answers your question. Were you about to follow up?
Oh no, not exactly. But it's I agree it's a hard question. But I'll leave it to that. Thank you.
Thank you. Any other questions? No one? So I have a final question, I guess. So you talked about the malware case, right? And you talked about the fact that, certainly the modified sample has to be still useful, right? And you explained how you can try to find such a sample. So I'm wondering if you have any thoughts about, is it possible for a system to learn how to look for that invariant behavior that really has to be there, right? Instead of being distracted by those additional nodes that you might add to the tree, or something else, right? Is it doable, and do you have any ideas?
I think so. So I think that what's suggested is, instead of saying you start with a sample that has the behavior you want and you try to perturb it to avoid the classifier, you start with a totally benign sample and you try to incorporate the malicious behavior into it, which also I think makes a lot of sense, and I think a lot of the manual malware construction is done kind of that way. I think that assumes you have a very good understanding of the malicious behavior you want to create. So one of the issues is it is easier to have a system where we can do experiments and recognize whether the malicious behavior is still there when we're starting from something that we know has it, than to end up producing it from scratch. But I think that definitely could work. We haven't done experiments in that direction, but I think it seems like if you could certainly start you're assuming you start with a description of the malicious behavior, so that's what you're starting with, and then you're mutating that until it gets classified as benign. I think if you built that from scratch, instead of using what you started from which was in our case, the PDF malware that embedded the malicious behavior in it, you would kind of have to construct a PDF file around it, which seems like a pretty hard genetic search problem. But at some level, you could say that, yeah, what we are really starting with is a description of malicious behavior that's wanted, because presumably the malware sample or the malware author who would be using a tool like this or that we're trying to simulate would start by creating the malicious behavior they want and then trying to get it to a state where it's classified as benign.
Okay. Any other questions? No? All right. If not, thanks again for the wonderful talk.